The bioengineering program at UT Arlington has provided education, research, and service for more than 40 years, offering PhD and master's degrees. More recently, an undergraduate bioengineering curriculum was developed and has already received ABET accreditation. Undergraduates can choose to pursue one of 3 tracks of dedicated curriculum in either biomechanics and disease, tissue engineering and nanomedicine, or medical imaging and bioinstrumentation. To give you an idea of some of the things you can do with bioengineering, let's take a look at the research going on in the department. Research led by Dr. Michael Cho utilizes tissue engineering principles to mimic brain tissue. Studies of brain injury are critically needed to address the increasing occurrences of trauma in the battlefield as well as in contact sports. By exposing the system to shock waves and determining the extent of tissue dysfunction, their model can help find out how blunt force manifests damage in brain tissue. Glioblastomas are an aggressive form of brain cancer which is able to infiltrate different regions of the brain. To begin understanding how these cancer cells can migrate so effectively into confined regions, Dr. Charles Chuang's group is developing biomechanical models to understand how the cell's traction forces can propel them into invasive migration. Understanding these mechanisms will help pave the way for new therapeutics. Most of us have known of a family friend or relative who has experienced a heart attack, which causes death of heart tissue and correspondingly a decrease in heart function. Dr. Jun Lau is looking to train the next generation of researchers to help fight cardiovascular disease. His group is developing new imaging methods for detecting early myocardial infarction and are also investigating strategies for regenerating heart tissue. The developmental formation of the heart has been known to be affected by biomechanical forces. To understand the effect of such forces, Dr. Ji-Hyun Lee is investigating heart motion using a technique known as light sheet microscopy. By looking at blood flow and heart biomechanics in zebrafish, they aim to gain a better understanding of congenital heart disease. While you may have heard of 3D printing of plastic parts, research from Dr. Jaworski's lab has demonstrated the world's first 3D printer of protein-based materials. Loading a simple pipette with high concentrations of proteins, like collagen, or even protein-based materials like virus, they're able to create custom layer-by-layer shapes. By guided extrusion, they can move the tip, leaving behind a trail of material. Because cells will stick and grow to these materials, this provides a new method for creating engineered tissues. To gain an understanding of how cells can interact with biomaterials, engineers like Dr. Yi Hong are looking to control the formation of healthy tissue by developing the next generation of biofunctional materials. In order to repair diseased or damaged sites in patients, his group is creating new biomedical implant materials, including gels and meshes, with the appropriate mechanical and bioactive properties for use in therapeutic tissue regeneration. Nanoparticles can offer an exciting drug delivery tool. Their surface chemistry can allow them to localize and aggregate on specific cells, while the interior can be loaded with cargo such as growth factors that can help to treat diseased tissue. In Dr. Ki-Tai Win's research, specially formulated nanoparticles are targeted to injured arterial walls where they can mimic platelet interaction toward the damaged wall and simultaneously deliver therapeutic drugs. Dr. Li Ping-Tang's group is working toward generating a cancer trap to lure cancer cells out of their hiding places where they can be destroyed without harming healthy tissue. They use biomolecules to entice cancer cells to enter a device that is implanted under the skin, resembling an artificial lymph node. This concept works like a roach motel for cancer cells in that a toxin is released inside of the device, and the goal being that the cancer cells can check in, but they can't check out. Research led by Dr. Youngtae Kim has shown that electrical impulses can be used to precisely modulate the body's neuronal circuits to reduce blood pressure and serve as an alternative to drug-based therapeutics. This strategy in treatment of hypertension is just the first step and can be applied to a number of other diseases that have yet to be explored. Dr. Alexandrakis' lab uses nanotechnology to build sensors that can detect the presence of single molecules and measure their size and electrical charge. This allows them to distinguish between different types of chemicals. They utilize microfluidics to deliver small amounts of liquid sample to the sensor. The sensor they built can be used for testing biological interactions, such as DNA binding by proteins or T-cell receptors engaging their antigens. While you may know it's important to get good sleep, Dr. Khosrow Behbahani's lab has taken it to the next level with his research on sleep apnea. Sleep apnea manifests itself as frequent sleep disruptions when the brain is exposed to large changes in blood flow or oxygenation. Under his guidance, the first automatic airway pressure controller for the treatment of sleep apnea was designed and built right here at UTA and has since been widely used in clinical therapy. Ultrasound switchable fluorescence is a new breakthrough in biomedical imaging to allow monitoring deep within human tissues. Typical ultrasound-based imaging may have weak resolution, meaning that one cannot really tell the difference between 2 points if they're too close together. However, by using focused ultrasound waves, Dr. Bao-Hong Yuan's group can cause a turn-on in fluorescence in tissues, allowing them to see object features as close as 100 micrometers and deep within tissue as far as 3 centimeters. If you're looking to enhance your memory, you might want to chat with Dr. Han-Li Liu, whose cutting-edge research has shown that stimulating your brain with infrared light can actually enhance blood flow and increase the efficiency of oxygen use by the brain. Her research is also exploring devices for imaging human brain functions, which will allow us to understand the developmental brain in babies, as well as the mechanisms of memory loss with aging, disease, or injury. Of course, all this research you have seen is done with the help of students. In the bioengineering department, the faculty and students work together to develop technologies and methods such as these that will fundamentally change how medicine is practiced. Whether it's summer research activities or involvement in research club teams like iGEM, there are plenty of ways for undergraduates to get involved and gain hands-on skills. In order to let students first get acquainted with how to carry out research and design, the Bioengineering department offers a number of computational and wet lab teaching facilities that host a range of different hands-on experiment courses. Here students learn fundamental techniques for characterizing, quantifying, simulating, and producing living systems as well as technologies that interact with living systems. Students will take this knowledge to formulate, build, and test new devices of their own during the Senior Design Project course. Here they'll work with advisors in the department on projects that will impact the field of bioengineering. This year-long team-driven project will integrate and apply all of the knowledge gained and concludes with the formal presentation of their project to an audience of faculty, students, and industry representatives. When it's time for graduation, students can look back at their friends and contacts they've made through the unique experiences offered through the department and student groups like the Biomedical Engineering Society to move forward into careers in the biomedical industry or furthering their education at graduate or medical schools. With all the new breakthroughs that have been happening in bioengineering in just the last year, it's sure to be an exciting future for bioengineers. We look forward to our UTA graduates being a part of the next wave of big discoveries and clever innovations that will help to shape the world that we live in.